Welcome back. Let us continue with our lecture on general theory of relativity. We have had some introduction to differential geometry, and we have defined connection coefficient. We can do a differentiation. We can define the generalized differential operator called covariant derivative on the curved space. Today we will cover the topic of Riemannian geometry. Connection so far not defined. First step is to define the connection and see if there is any relation with the physical quantities. And once that is done, we will end up into Riemannian geometry. So today's topic is Riemannian geometry. This is a part of a course PH4205 at IISER Calc. Let's first recollect the definition of covariant differentiation. So far, our first step forward away from the flat space-time has been the definition of covariant differentiation. The covariant differentiation on a vector field is defined as, we call the covariant differentiation as nabla. Various people give it a various name. Sometimes it is used colon. Here mostly we follow a easier notation. Covariant differentiation of a covariant vector is defined as a partial differential of that vector or a gradient of that vector minus gamma dot TP, the contraction of connection coefficient gamma PAB taken a dot product with the vector itself, that is TP. Now we can also define the covariant differentiation of a contravariant vector. Again, that is defined as nabla. Covariant differentiation of TQ is given as a partial differential of TQ or dTQ by dXA plus contraction of a connection coefficient with tensor component of vector T. Now the gammas are connection coefficient. It is a non-tensor quantity and we can say that it is not unique. Once we have a tensor quantity, that only forms a form invariant, or it would be transformed easily from one coordinate system to another coordinate system. When we have a non-tensor quantity, it need not be unique and it can have a whatever form it like to be in different coordinate system. So this keeps it a whole topic little vague. In fact, we have not defined it, and each gamma we defined, we can associate a covariant differentiation with this formula, and we also know how the gamma symbol should transform. So that is why the gamma and the covariant differentiation are closely connected. For every gamma, you will have one covariant differentiation. So that means the concept of covariant differentiation itself is not unique. We can have as many covariant differentiation as we want. So this makes the whole topic little vague. But let's proceed with extending the covariant differentiation to arbitrary higher rank tensor. So let's look at the covariant differentiation of second rank covariant tensor. That is a differential operator acting on a second rank covariant tensor. Then you will see first the gradient of that or the partial differential of that tensor, and then because you have two vector indices now, this can be treated as outer product of a two vector quantity. So you take a dot product of gamma with each of these covariant indices. So what we have is a gamma P AB TPC minus gamma PAC taken dot product with the TBP. So same way we can define the covariant differentiation of second rank contravariant tensor. Again, we have a differential operator acting on a contravariant second rank tensor, giving a first term would be the partial differential of a same tensor with the coordinate XA, and then we have two tensor indices, contravariant tensor indices. Each of them should have a one gamma, otherwise they would not transform like a tensor. So we contract with the gamma coefficient, that is a gamma BAP taken dot product with the TPC plus gamma CAP taken dot product with the BP. So corresponding tensor indices get contracted, and that is how we define the second rank tensor. So we could have a mixed rank tensor too. So we have one covariant and one contravariant tensor, differential operator acting on this. First, we have a partial differential or gradient of that tensor quantity. Then we have two terms which are coming from each covariant and contravariant component taken dot product with respect to the connection coefficient gamma. That is gamma BAP TPC minus gamma PAC BTP. So this way we can extend this definition to the arbitrary rank tensor. Each tensor indices would have a corresponding gamma term. Plus or minus sign is decided by whether it is a contravariant component or covariant component. Each covariant component get a minus gamma and each contravariant component get plus gamma. Let's go ahead. So what we have defined covariant tensor, and then we have this connection coefficient. The question is there some way we can connect gamma to the metric itself? Because eventually we want to express everything in terms of metric. That is what happens in the general theory of relativity. But ideally you would want to ask this question whether gamma can be related to metric. It may or may not be related, but what does convenience it does offer, whether it offers some constraint on gamma so that we can easily compute the gamma coefficient as well as connect it to the geometry. This is the same thing we have done with the covariant and contravariant vector. We know that they are dual to each other. There need not be any connection between them, but we decided covariant and contravariant vector should be connected with the metric tensor so that we can easily raise and lower the tensor, or we can easily transform covariant tensor to contravariant tensor. The similar idea can be proposed here. One of the idea is that once you define your covariant differentiation, whether we can take the covariant derivative such that our metric tensor remain constant with respect to that covariant derivative. That is, the covariant derivative acting on the metric tensor, either covariant component or contravariant component, should be equal to 0. That means metric is constant with respect to our new differential operator. One reason for doing this is inspiration comes from the flat space-time. We have that the Minkowski metric is constant with respect to partial differential. That gives condition that the d eta AB by xp is equal to 0. So now we have generalized our differential operator. Can we generalize this condition such that covariant differentiation of a metric tensor is 0, or that what does this lead to? There is another reason that let's start with differentiation of a covariant vector. Now we know that in our case we have assumed the relation between the covariant and contravariant vector through the metric tensor, and that means the inside whatever covariant tensor we have, we should be able to represent in terms of a contravariant vector and a metric tensor, that is GAB taken dot product with the TB. Now we have to use product rule. Then we see that we get two terms. First, GAB remains same and our differential operator acting on contravariant tensor TB, and then we have a contravariant tensor comes out and our differential operator acting on the metric tensor GAB. Now this leads to two terms, which is annoying. In fact, when you want to raise and lower index as relativists do it very often, you would find that each time you differentiate, you will end up with having an extra term. It can lead to very complex expressions, and the best way is simply get rid of this term. And then we say that the operation of raising and lowering indices can simply be done inside or outside differential operator. It makes no difference because we have assumed the differentiation of metric tensor is 0. So this is a main advantage which leads to simplification. Eventually we want to have a simplest mathematics which could express the laws of physics. We do not want unwanted complication in the mathematics itself. It might obscure physics which we want to express. This brings us to the Riemannian geometry. The Riemann came up with the idea that we could assume the covariant differentiation operating on the metric tensor is 0. In addition, he also proposed a constraint that the gamma AB in the lower indices should be symmetric. Once we impose this condition, what we get is a Riemannian geometry. The Riemannian geometry is based on the connection. Assume that the metric GAB is constant with respect to covariant differential operator and the connection is symmetric in the lower two indices. Once we assume these two conditions, the geometry which we have now is called the Riemann geometry, which was first proposed by Riemann. Now onwards, we will be studying only Riemannian geometry. Unless and otherwise explicitly stated, we assume that the covariant differentiation of metric is 0 and the gammas are symmetric in the lower two indices. It is possible to have a full geometry without this condition is assumed. Your gamma need not be symmetric in the lower indices. This leads to what is known as a torsion, but that is a much more complicated geometry. Einstein stuck to the simplest possible geometry, that is the Riemannian geometry, to explain the phenomena of gravitation. Connection in Riemannian geometry. Once we impose the condition that the metric is constant or a differential operator acting on the metric tensor is 0 and the connection coefficients are symmetric in the lower indices, we may end up with some simpler relation between the metric and the connection coefficient. That is what we are going to compute and see whether there is an explicit relation. Let's start with the explicitly writing the condition that the covariant derivative of a metric is 0. So this we can express. We know how to take the covariant differentiation of a second rank covariant tensor. Let's explicitly write down that the differential operator or covariant differential operator acting on a metric tensor, first term we get is a partial differentiation and two terms would be connected with the connection coefficient. Carefully note the indices in the various terms. This is going to play an important role. It is a bit of a jumble of the indices, but it is how most of the calculation in GR works. So carefully see, you have a differentiation, partial differentiation with respect to index P, and that comes here and here. Then we have two indices of metric which comes from GAB. This is just a partial differential, so GAB would be here. The first term would be the first indices, that is A. So you have A comes here and P and Q, and B is the free index. Same way B would be replaced now by A, and then you have PB, Q and Q here, and A would be there. Our plan is to exploit the symmetry of gamma in the lower indices, that is gamma A upper, BC lower should be equal to gamma A upper, CB lower. That means it is a symmetric in the lower indices. Let's take the cyclic permutation of index PAB in this expression. We have three indices P, A and B. We are going to exploit this relation. So we got to jumble up all of them in a cyclic order and then write the expression. It's an identical expression written 3 times. It doesn't matter. The expression is 0 here because covariant differentiation is 0. So we can rewrite in the any index form by calling it in the different name, and then the relation won't change. And that is a 0 tensor in all the reference frame. In this case, we take the cyclic permutation of indices P, A and B and see any simplification happens. The second one, it need to be carefully written down. P becomes A becomes B, and B becomes P. In all the following equation, this would be done other than all the dummy indices. Q would remain Q in both expression, but A would becomes B, B would becomes P, and P would becomes A. That is what is done from this to this transition. That is one cyclic permutation. The second cyclic permutation from this to this is again A becomes B, B becomes P, and P becomes A. So that becomes covariant differentiation with respect to B. Again in this expression, the dummy indices remain same, and we repeat, A becomes B, B becomes P, and P becomes A. Once we do this transformation for each of these terms, we get these cumbersome equation. It is impossible to grasp this when somebody is talking in words. Only way is you have to write it down carefully and note. And these indices can be very confusing. But of course, let's go ahead. I'm assuming that you are all writing. If you are not writing, you will have to come back and write it again. So we are going to exploit this condition. Let's see if any terms which match with each other. So let's look at this term and this term. So here we have a Q is a dummy indices. We have a PB here and BP. But this condition imposed that first term would be same. Let's look at the second term. We have a GAQ, and in the second term we have a GQA. But a metric tensor is symmetric, so these two are same term. That means this term is also equal to this term. Now let's look at any other term which is matching, and let's look at this term and this term. We have a dummy indices Q, and then gamma has a A and B. Here gamma has a B and A. Again we exploit this condition, then the first term would be same. Second term is in terms of metric. Here the index is QP and here index is PQ. So they should be symmetric and they should be the same. So this expression should be equal to this. Now only two terms are left. So let's see what they are. Let's compare these two terms and see whether we find them same. First per index of gamma is Q, which is a dummy indices. We don't have to worry about it. Lower index of gamma is P and A in this case. In this case it is A and P. So once we assume they are symmetric, it is the same. The metric index here is a QB and BQ. So metric is symmetric and these two are same. So we see that these are distinct terms with the different partial differentiation of a metric tensor, and some of the terms, because of the assumption which we made, they are repeating. Now we can take a combination of this. Let us number this equation 1, 2 and 3, and let's take a combination 1 plus 2 minus 3. Now we get this expression. Let's go through this summation very carefully. We have seen that these two terms are same. Now they come with the opposite sign because this last term gets subtracted from the first two terms. So these two cancels out, and the same way the last term gets subtracted from these two. So these two terms cancels out. So we left with the green term, that is two of them. So 2 gamma Q PA. Because this side it is 0, so we are going to take it on other side. That's where the minus sign is taken care. So this side is 0, so we are not worried. This is the expression which we assume to be 0. Covariant differentiation of a metric tensor is 0. So we take this term on the other side of the 0, and then we get it to be positive. Now all these partial differential, they come up with the same combination. First term you have a GAB taken the differentiation with respect to P, and GBP taken differentiation with respect to A, and GPA taken the differentiation with respect to B. So this is what we get by taking this combination. It's all about to cancel out the repeated term and get the expression for gamma. Let's go ahead and further simplify this term. We have this condition and this is the result we have got. Let us multiply both sides with the GBR so that we get rid of this term. So this essentially is done when we multiply both sides by G, B and R. So we get a term like QB by GBR. What we end up having is a delta RQ, and the Q index get replaced by R, and finally we end up having a relation gamma RPA is equal to half GRB into partial differential of GAB with respect to P plus partial differential of GPB with respect to XA and minus partial differential of GPA with respect to XB. Now this is somewhat muddled up equation. We rewrite some of the dummy indices and make it look neat, and eventually we get the expression for the connection in the Riemann geometry in terms of metric tensor as a gamma ABC is equal to half GAP into partial differential of a metric PC by XB, and the partial differential of a metric PB with respect to XC minus partial differential of a metric GBC with respect to XP. So this is a connection represented in terms of a partial differential of a GAB. This expression is valid in the Riemannian geometry. The Christoffel symbols. In Riemannian geometry, the connection coefficient can be expressed uniquely in terms of a metric GAB and its partial differentiation as this expression which we have derived earlier, and these symbols are called the Christoffel symbols. The connection in the Riemannian geometry has a special name and it is called the Christoffel symbols. Of course, we know that they cannot be metric tensor because they are expressed in terms of a partial differential with respect to metric tensor. Partial differentials do not transform like a tensor. So this is how, once we get Christoffel symbol, we can do covariant differentiation in a given Riemannian geometry, and that is where now we get into more practical way of doing Riemannian geometry. You have a homework, problem 1, homework 3, derive the expression for the gamma ABC in the Riemannian geometry in terms of the metric. And the deadline is 10th February 2021 at 6 p.m. This is essentially the mix-up or the soup of indices which we have done in last couple of minutes. Let's go ahead and let's take an example. The example is to compute the Christoffel symbol for a Riemann space given by the distance element ds square is equal to d theta square sine square theta d phi square. So you all know this is a metric on a two sphere where the coordinate x1 is given by theta and the coordinate x2 is given by phi. So you see that the metric doesn't depend on phi, so some of the calculation would become much easy. And also metric tensor is completely diagonal in 2 dimensions. It's a 2-dimensional space. So metric can be written in terms of matrix with the diagonal element 1 sine square theta. The inverse metric in this case can be very easily calculated. GAB upper is 1 and 1 by sine square theta. We need to now compute gamma ABC. Now gamma ABC, we have indices A, B and C going from 1 to 2. Now let's calculate gamma 1BC. We get half G1P into all this expression. Now we immediately notice that this is a diagonal matrix. So we have only component comes with 1 is a 1 1 only, so other things going to be 0. So we can simply write down this as a half G111 and all the index P becomes 1. That is in this case, first case, G1C differentiated with respect to XB, G1B differentiated with respect to XC and GB differentiated with respect to X1. But the first component X1 is a theta, metric is dependent on theta, so we cannot further simplify this. Let's compute the individual component. Let's compute the element gamma 11C given here. So we have a G11 and B becomes 1. All the B here becomes 1. First one become differentiated with respect to X1. Second one remains same, G11. Third one is B becomes 1C and differentiation with respect to X1. So now we see that the G11 here is a constant. So if you differentiate with anything, it is going to give 0. So we can get rid of that term. So we end up with having a term of G11 differentiation of G1C with the X1 minus differentiation of G1C with the 1. Now we calculate two terms. C would go 1, 2. So the first term is gamma 1, 1, 1. That is half G11 multiplied by G11 differentiated with x1 minus G11 differentiated with respect to x1. With my limited image processing, it says that this should be 0. Let's put that to 0 and let's compute the next term, gamma 1, 2. Gamma 1, 2, let's calculate this half, and G12, this is going to be 0. G12 again, that is going to be 0, and this is again going to be 0. So it looks like that we foolishly did this calculation. Sometimes when you blindly follow the rule, this is what happens. In principle, you should have noticed that this term is subtracting A with A or B with B or C with C, and it should give 0, and there is no need to do this calculation, and all of these are equal to 0. So keep an alert eye on different term and indices when you do calculations on Riemann geometry. This is exactly the demonstration. It is not good to blindly implement the rules, but keep simplifying as you go along. Let's compute the remaining components. Again, we have G12C, that is the term which we want, and that again we can express with this equation, that is a half G11, G1C differentiated with x2, G12 differentiated with the xc, and G2C differentiated with the x1. First term is going to be 0 because no metric depend on the phi, so x2 is phi, so we get rid of that. And the second term is also going to be 0 because there is no off-diagonal element in your metric, and we end up having a one single term, partial differential of a G2C with the x1, which is a theta. So we can compute this. The first, there are two more terms here. Gamma 21 is equal to half G11 minus gamma G21 x1. That is going to be 0 because this term is 0. And the second term is actually differentiation of G22 with respect to x1. x1 is theta here, so we simply have this term non-zero, and then we end up having a term which is the 2 cancels out, and gamma 1, 2, 2 is equal to minus sine theta cos theta. So this looks like there are a lot of indices to be calculated. Again, we should see here gamma 2, 1 we need not have to calculate because we have already calculated gamma 1, 2, which is 0. Because of the symmetry property of a lower indices, we didn't have to compute this. We should in principle see during the calculation. I am doing it again to show that where you have to keep your eye open, especially when there are symmetries, you can reduce a lot of calculation. Let's do the next term. We have done upper 1, that has been done. Then we have upper 2 and then lower again BC. Again, we expand them. We have a expression for gamma 2 BC. We can take G2P, and we note that it is a diagonal element. So only non-vanishing term is a G22, and then all the P is replaced by 2. So, but this term has to go to 0 because metric is not dependent on a phi coordinate system, so that will go to 0. So we end up a little simpler equation. We have gamma 21C is equal to half G22, differentiation of G2C with the x1 and differentiation of G21 with the xc. Again, this would be 0 because no off diagonal element, so we end up gamma 211 is equal to 0 because it is a differentiation of 0 with respect to theta. So there is nothing left there. We can now compute. We get gamma 21 as a half G22 into differentiation of G22 with respect to x1, that we know that 1 by that is a sine square theta. Again, these two terms cancels out because G upper to 2 is sine square theta, and then we end up having a gamma 2, 1, 2 as a cot theta. So this is a somewhat nasty calculation even for 2 dimension. Then you think of what would happen to 4 dimension. So we see that our non-vanishing term gamma a, b, c. So we have split into terms. This we write it as a gamma 1 bc and gamma 2 bc. So each of them are now second rank tensor. So we can represent in terms of the matrix. So that is what we have given here. So the first one is gamma 1 AB, that is this matrix which has only gamma 2, 2 which is non-zero, and the second one is given here which is gamma 2 AB. Again it has a off diagonal term and zero diagonal term, all because of this calculation. So these are the non-vanishing components of connection coefficient in the Riemann geometry of 2-dimensional sphere. Now this looks very cumbersome. Let's count number of components or a number of elements in the Christoffel symbol. Christoffel symbol has 3 indices, so it should be having in an n-dimensional space, it should be having a n into n into n number of elements. However, we have a symmetry in the lower 2 indices. N square would be replaced by n into n plus 1 by 2. So this is a standard calculation of number of element in a symmetric matrix. So we end up having a total number of independent indices are n into n, n plus 1 by 2. So this is number of component we have to calculate based on the various symmetry. Specific cases, some of the term might be 0, some of the term will remain, and that is what we have. In the case of a flat space-time, metric doesn't depend on the coordinate and you will have all the gamma terms 0. So that is a simple case. When we go metric component depend on the coordinates, then you will have gamma non-zero. Even a simple case as a spherical polar coordinate system, you would find that gamma coefficients are not 0. But we are not doing that simple calculation. We have done it on a sphere. Now there is another homework, which is homework 3, problem number 2. Derive the expression for gamma a, b, c for a Riemannian geometry. The metric is given as a d chi square plus hyperbolic sine square chi d phi square. Here x1 is chi and the sine theta in the sphere has been replaced by hyperbolic sine chi. So you have to calculate the connection coefficient or Christoffel symbol for this metric, and the deadline for this homework is on the 10th February. This is the second problem for the homework 3. So you have a deadline on the 10th February at 6 p.m. Let me stop here and continue with the next lecture, more details about the Riemann geometry.